recording.
Okay.
And so we're very glad to have Wieslaw Kubis, hopefully that's the pronunciation, talking today with abstract evolution systems. So you can start when you're ready. Thank you.
Okay, thanks a lot for invitation. So it's a real pleasure to give a seminar talk. Of course, I would be even more happy if it was in person, but that's the life. So in any case, yeah, I would like to talk about some concept as it is in the title, which I had this concept in mind for a couple of years already. For a long time, I thought that, well, maybe it is something like, well, it's very simple. This is, you will see that the notion of evolution simple system is actually something like, well, it's a category with some extra structure, so really nothing special, but it turns out relatively recently, especially when I started to discuss, even teach this concept to my new PhD student, who is the co-author of this work, Paulina Radecka, okay, and she brought some examples of natural evolution systems and so on. So, okay, let me start with something like, looks like a different topic, generic structures, namely. So this is something I'm working on for several years already. And it is like the motivation for introducing the concept of evolution systems, okay? And okay, I have some very informal definitions. By the way, I have some slides here, but my idea is actually to make some handwritten notes on the screen and draw some pictures, etc. So at some point I will have to switch to another viewer, to editor, yeah, which allows to draw. For the moment, I will just show the slides. So yeah, informal definition. What is a generic structure? It's formally like something occurring typically. You can think of probability one or, you know, Baire category theory and things like that. But I would never say a structure is generic if it is built in the most complicated way from some small pieces. Yeah? What are the small pieces? Some approximations of the structure. So you think of, say, model theory, small pieces are finite structures, and a bigger structure is something which is the union, colimit, or something like that. Okay, this is a very vague definition. It's not mathematical so much. Yeah, the second one is like most often, and more, occurring most often could mean that you impose some probability when you are building the structures, and most often means with probability one or highest possible probability if it's not one, and or largest, yeah. And another thing that, for instance, you have some topological space of structures which is complete, and most often could mean that it contains a dense G delta, yes, residual set. It also makes sense, and some people looked at it. Okay, I would like to, maybe I will not talk too much about this game here, but let me just mention this. This is my favorite definition of a generic mathematical structure. Namely, we have a game. So we imagine some class of small structures. So formally, this is a category, yeah? Our favorite category whose objects are some small structures. I mean, small is just a name. And we play the game in such a way that player one starts with some structure, some object from our category. Then player two answers with something bigger. What does it mean bigger? That there is an arrow from the from the first structure to the second. And when player one answers with some arrow to something bigger, yes, imagine that arrows are some sort of embeddings, at least monomorphisms. And when these two players, after infinitely many steps, they are building some, I wrote, well, I use these slides for a presentation to some more general audience. So I use some names which are maybe more familiar, like a tower, yes, but it's really a sequence, or a chain of small structures, formally a functor from the natural numbers. And now we can test its colimit after all, yes, which is very often the union or some completion of the union, etc. And we may say that a mathematical structure is generic, of course, with respect to a fixed category of some sort of embeddings, if the second player has a strategy which always gives you this structure. Yes? So he can play in such a way that you will always obtain in the end a structure isomorphic to U, to this capital U. Okay, I will give some historical examples so that you will see how it works. Now, all these generic structures, their typical examples are called Freyse limits. So I have some slides with the history. The first one, as I see it now, this slide is a little bit, how to say, obsolete. So there is some history where people, mathematicians who discovered or studied generic structures. So Cantor discovered that the set of rational numbers is unique with respect to some basic properties. This will be on the next slide. Urison, who was a topologist actually known for developing dimension theory. However, his last paper published after his death was about with the construction of a very nice universal homogeneous separable complete metric space. And it's a very nice example of a generic mathematical structure. I mentioned the name Freyse, so probably many of you heard the name Freyse limit. He was the one who developed, abstract, model theoretic theory of universal homogeneous structures, definitely motivated by Cantor's theorem. When Johnson was extended it to uncountable sizes, arbitrary uncountable cardinalities under some cardinal arithmetic assumptions, then only in the 90s it was Droste and Gebel who did this thing in category theory, actually repeating Johnson's assumptions, encoding them in pure category theory, obtaining some new examples. Then, there's a work by Irwin and Soletsky where they simply reverse the arrows. Oh, sorry, I have to close something because it will disturb me a bit. Okay. Now, Let me check. Okay, so these dots really mean that there are several other works, including mine, which I'm not going to mention. Yes, these examples. So the set of rational numbers, when you view it as a linearly ordered set, could actually look at it as an abelian group with the addition, with plus. It's also generic, but it's in some completely different category. Here, you can guess what are the small structures, objects, finite subsets, finite linearly ordered sets. So we can play this game The first player starts with some finite linearly ordered set. The second one answers with some bigger linearly ordered set, and so on. So what the second player can do, he can simply, at each step, he can add a new point between any two existing ones, right? Also one extra point at the very beginning, one extra point at the very end. And by this way, when they, after infinitely many steps they play, they obtain, I mean, the resulting set is a linearly ordered set which has the property that between any 2 points we have another one. There's no minimal element, no maximal element. And this is Cantor's theorem saying that such a set is isomorphic to the rationals. Yeah? And the standard proof is simple back and forth argument. Okay, then this is what I mentioned, Urison universal metric space. Not only universal, actually, it has this nice property that every isometry between finite subsets extends to a bijective isometry. There's a little bit less trivial to show that it is generic. Well, in which sense? Our category now is consists of all finite metric spaces, right? And the arrows are isometric embeddings. Now we are building, in the game, we are building a chain, and in the end, we are not taking just the union. We are taking the completion of the union, okay? And this is the co-limit. So we are, our bigger category is the category of complete metric spaces. And in fact, the second player has a strategy leading precisely to this particular space. Okay, then something quite well known, I mentioned here Rado 64, the Rado graph. It's also called the random graph because it was independently discovered by Erdős and René when they were studying random processes leading to infinite graphs. That is a graph which is, again, like the previous ones, it contains all possible finite graphs, and every finite isomorphism extends to an automorphism. Then, if you want something more algebraic, Hall's universal locally finite group, discovered, constructed by Hall independently of Freysse. Well, Freysse actually in 54 used relational structures, but it's not so important. You allow algebraic operations, it is still fine. And here, if you look, okay, so this is a locally finite group, countable locally finite group. Locally finite means every finite subset generates a finite group, yeah? And if you read the paper, the original paper of Hall, so he actually has a very simple strategy of constructing this group. At each step, you just embed your finite group into the symmetric group of the set. Yeah, so you have permutation groups. You have a finite group G. You forget the group structure. You take all permutations of G. Left translates actually are permutations. Yes, so this is the embedding. Once you repeat it infinitely many times, you always get the same group. And it is again homogeneous, universal in the sense that every other countable locally finite group is inside. Homogeneous in this sense is even stronger than, well, it can be stronger, and it is really that every finite isomorphism extends to an automorphism which is even inner, so represented by a point. Okay, then something from Banach space theory, yes, the Gurari space. So this is something, yeah, generic Banach, separable Banach space in the sense of the game as well, although Gurari didn't know it this way. just constructed it, and it turns out to be homogeneous with respect to finite dimensional spaces. However, the homogeneity is with some errors. Okay, it's not like every finite dimensional linear isometry extends to an isometry. It can only be approximated, arbitrarily close. You find an isometry, but this is actually sufficient to conclude that such an object is generic. But when we are going more to something like metric enriched categories, which I'm not going to discuss so much, then there is some analogous object in C-star algebra, phrase the limit of so-called UHF algebras. I'm not going to discuss this. It was built before 99, I think, but it was discovered as a generic structure, phrase a limit in a proper setting. Then there are several, actually infinitely many examples in, say, geometric topology. Maybe the first one, the Cantor set, is not so much geometric. Its geometry is pretty poor, but it's actually, you take the category of finite non-empty sets with surjections, yeah? And so the arrows are reversed. An arrow from X to Y is a surjection from Y to X, onto X. And let's say that you play the game, so we are building an inverse sequence, yeah? And the second player can build or can answer each step in such a way that the surjection has, how to say, splits each point into two. The fiber of each element is at least two, yeah? And then at limit you get compact zero-dimensional metrizable space, which with no isolated points, and it's well known it is the Cantor set. Yeah, there is only one like that. And here, homogeneity is actually different than in the previous examples. Namely, you have any finite any partitions into Klopen sets, okay, which they must be finite, of course, by compactness. And then every bijection between such partitions can be lifted to a homeomorphism, moving, of course, preserving the partition. It's actually the Cantor set. It's better maybe to see to use stone duality and look at Boolean algebras. Yes, finite Boolean algebras and then countable atomless Boolean algebra. Then you see homogeneity, universality, and so on in the usual way. Okay, the other examples are like, well, the pseudo arc is some very interesting compact connected subset of the plane. But nobody can see it really. Yes, it is connected, compact, and whenever you find two connected compact subsets, either they are disjoint or one is contained in the others. This is called being hereditarily indecomposable. And yeah, again, it is unique with certain properties. This is what I mentioned, these names, Irwin and Soletsky. They actually discovered it as a generic structure, looking at some category of graphs and taking a quotient. And I'm writing a paper which should have been finished some time ago already with Adam Bartosz, where we are doing it directly and studying some more properties of this, but okay, never mind, it's another story. Other things are like, yeah, the Lelek fan is some very nice subset of the plane, which consists of line segments, which looks like a fan or something like that, yeah, and there's some extreme properties, but okay, since the time is running, I would not go into the details. Maybe the Paulsen simplex is quite interesting. It is a simplex in say, the Hilbert space. So a convex compact set, which whenever you cut it with a finite dimensional space, you really see a simplex. So if you cut it with a plane, you always see a triangle, okay? And it has the property that extreme points are everywhere dense. And again, you can see it as something generic. So as you see, these examples are from quite different areas of mathematics even. Yeah, the Warzewski dendrite is some sort like a tree, looks like a tree. It splits in many places, and then again, you really apply the definition of this particular dendrite, you get uniqueness, etc. So I think that in this, I'm not going to talk about the theory of generic structures so much, only as motivation actually, but it is very interesting that you have some general simple properties of some structure which actually give you uniqueness up to isomorphism. And this is what I find really good and applicable. Okay, in any case, let me just continue. So it is, how do I say, yes, as I mentioned at the beginning, this is joined with my PhD student, Paulina Radecka, who I'm afraid couldn't attend this seminar because of some other duties, but okay. What I wanted to say, yeah, so we have a definition now. What is an evolution system? And you may be a bit surprised or even at the beginning disappointed because it's a very simple structure. So 3 parameters. At some point I will need also one more parameter, but maybe not today. Okay, this, in the end I will mention what else is required if you want to do something more. But for the moment, it is like this. You have a category. It's the letter should suppose be V, which is some, let's say, is the category which in which we are working. Yes, so it is, say, sufficiently closed. Let's say that every sequence has colimit, for instance. Yes, typically we would like to have these assumptions, and practically nothing more. Maybe the last parameter, which I call theta, is a fixed object, and we call it the origin. It's like an object we start with when we are, for instance, playing this game mentioned before, or actually creating any evolution. If you want it could be an initial object, but it doesn't have to be. There are absolutely no requirements here. And well, the important thing is that we select a class of arrows, yeah, and we call them transitions. And yeah, my first motivation for this was actually the fact that when you deal with classical model theoretic Fraser limits, when you have, let's say, relational structures or even algebraic ones, it is very often, for instance, you prove amalgamation property, things like that, people really consider one-point extensions, right? So what does it mean? You have a structure, finite or finitely generated structure. One-point extension is that you are adding one extra point and you generate, yeah, whatever you get. And also isomorphism. I think, yeah, the only requirement which I think really should be added. So let's say this is like the only axiom, I would say, yeah, that every isomorphism is a transition, okay? And isomorphism will simply move from one object to another, which is really the same from the category theoretic point of view. We should be allowed to move this way. Now, what is, once we have this very simple setup, the notion, we can look at something that I call evolutions. By the way, I checked, let's say I searched the internet whether there is any mathematical notion which is called evolution system, and I couldn't find. So by this way, there should be no confusion with existing literature. And if you think that evolution has something to do with biology, it is not completely true, because evolution has also an abstract meaning. At least I checked in the free English dictionary. So I don't find any problems in this particular name. And now, in any case, an evolution is simply a sequence of transitions, okay? Starting from the origin. That's it, nothing more. Now, another thing is that when we are considering evolutions are supposed to be infinite. So we will also need finite compositions of transitions, of course. And I decided to call them paths, okay? Even though the name path can be a little bit confusing in the sense that if you look at transitions as a directed graph, yeah, then a path would be a sequence of transitions. And for me, it is a composition. Wait a second, I have to disconnect. Maybe I have to disconnect the phone. It's the best, because somebody is calling when I am busy. Okay, fine. I hope no other problems. Yeah, so a path is simply that you take some object from your category, then you take one transition, another, and so on. So in particular, paths can have some length. The point is that you can have a path, let's say, of length 3, composition of 3 transitions, and then you may realize that actually 2 transitions are enough. Yeah, it's like there could be several sequences of transitions which give you the same. That's obvious, yeah. Okay, so you see, now I would have to switch to the other one, but okay, maybe I will skip the picture for later. Yeah, let's continue, because I was prepared for drawing some picture. But I think since this is an algebra seminar and people are working in category theory, then I don't need to visualize what an evolution system is. Okay, maybe instead of this, let me just say, just go back to the definition. So you can notice that first of all, tau, since there is no requirement about tau, tau could be a subcategory of V, or even tau could be equal to V. Yes, so it's so general that it really covers everything. Interesting examples are where tau is properly chosen. Yes, like this, what I said, 1-point extensions. So V could be, okay, you fix your favorite language, let's say first order language, and V could be the category of all structures in this language with homomorphisms, if you like, or embeddings, if you prefer, maybe all homomorphisms. Then transitions could be simply 1-point extensions. Yes, embeddings with the property that the image is, like differs by 1 element at most. Yeah, and then the origin, typically the smallest possible structure, could be the empty one if it is relational. Some trivial structure, yes, if it is, for instance, in the category of groups, would be trivial group, trivial ring, if you prefer, 0, 1, etc. Trivial Boolean algebra, yeah, if we talk about Boolean algebra, so 2-element one, or something really bigger. This is possible. Okay, now, yeah, an object is finite if there is a path from the origin to this object. So there's some abstract notion like this. I could really call it finitary or something like that, but I would never say a finite set or something like that, because this could be confusing. Finite object, yeah, so reachable by a path from the origin. And now the point is that I want to present the result of, about, say, generic evolution and generic limit of this evolution. Now, the crucial thing, in my opinion, is what I call finite amalgamation properties. So, yeah, again, I was supposed to draw a picture here. So maybe in this case, I would try to stop for the moment and share the other stuff, okay? I mean, the other editor. Let's see. Yeah, and you see now there is this problem with you see the green line in the middle, right? Or only I see it?
We see it too.
Yes, so I wonder what, because I had this problem, and if you pause the recording for a while, yes,
Okay.
and I will stop sharing maybe.
Okay.
Right, so yes, it's a bit smaller, but at least now I can draw. So first of all, amalgamation property for a category would mean that you start with some object Z. You have two arrows, and you can close this diagram, yeah, with another two arrows. Something, somewhere, yeah. Now, so first of all, if I defined it this way, then I don't need the concept of evolution system anymore. Yes, this would be really purely category theoretic. So I really want something that relies on all parameters. So I call it finite, first of all, because I assume that this is finite, this one, and the blue arrows. So actually, I will correct the picture. Actually I don't have any idea for how to denote transitions in diagrams. Yeah, my only idea is to make them short. Yeah. So F and G are transitions, and then I assume the finite amalgamation property says that you have two transitions, and you actually are able to close this diagram again by, some W, let's say. And these two arrows are again transitions, yeah? So F prime, G prime are in tau. This is important. Because you may expect, and I will talk about it later, you may also expect that these F prime, G prime are just paths, yeah? You start with transitions and you close by paths. Unfortunately, this is not good, because you cannot prove that you cannot get amalgamation for paths, for the, paths between finite objects. Yes, I forgot to say this. If you take all finite objects with paths, this is a category, yes? And I would like to get that this category has amalgamation property. And from the finite amalgamation property, I get it, yes? So I have this place, so I can now draw. Now, okay, so let's say our evolution system was E. So let's say that E fin would be the category of all finite objects plus paths, yeah? So an object is something that can be reached from the origin by a path, yeah? And arrows between two objects are again paths. Now you see, when you start with something and you have, let's say, a path of length 3, and when you have another path of length 2, by the finite amalgamation property, you close this square here by path, by transitions. Yeah, these arrows indicate transitions. Now you close this diagram by transitions, this one, and so on. Yeah. Oops, sorry, it is a little bit in the wrong place here. Yeah, you close this. So you see, if you have a path of, let's say, length 3, another path of length 2, you can close it in such a way, amalgamate in such a way that on the opposite side you have length 2, like here, and here you have length 3. This is the result. So a very simple induction which will actually work. So the claim is that Affine has the amalgamation property. Okay, if E has the finite amalgamation property, then this is actually the claim. Yeah, I also had in mind maybe to show some basic examples of amalgamations, but well, it's like 20 minutes perhaps. Yes. So yeah, just a very simple picture, just in case. So you have amalgamation in case of finite structures, let's say with embeddings, means that you have like you have some structure, you have some embedding into something bigger, typically 1-point extension. Yes. Then you have another one point extension, and you should be able somehow to merge it together. Yes, maybe identify something and so on. So if you look, for example, at finite metric spaces with isometric embeddings, they do have amalgamations, and actually the best way to prove it is to use 1-point extensions, which would be our transitions. Yeah. Okay, so in any case, this is more or less about amalgamation. Now I can, yeah, by the way, when I draw, you see my ceiling on the camera, I suppose, but this I cannot help. Okay, now, there's one more thing which I haven't defined explicitly. Yeah, because the slides come from some shorter talk. That is why I didn't have time for doing it. So now, but you may actually guess what does it mean that our evolution system is essentially countable? Namely, first of all, from the origin, you start from the origin and you see countably many transitions up to isomorphism. Okay, I will draw a picture a bit later and to make things clear. What does it mean up to isomorphism? Then you use one of the transitions, then again you see countably many. Okay, so in the more formal definition is that for every finite object, you have countably many transitions from this object up to isomorphism. So actually I can use this slide to draw, because this gray area is free. So you have a finite object. So here is the origin. You have some path to this object. And here you have transitions. You may have really plenty of them, but you can always select countably many among them, such that any other is isomorphic in what sense? In such a way that I'm thinking about the proper color. And for instance, blue is isomorphic to something green in the sense that I can get an isomorphism in this way. Yeah? So isomorphic in the on the codomain side. Okay, so this is what I call essentially countable. Now, think of these examples from model theory. If you take finite relational structures in a finite language, and transition is one point extension, yes, when you have it, yeah, it is essentially finite even, yes, because you have, say, a structure which has 10 elements. You want to add one more, but your language is finite, so you have actually finitely many possibilities. With algebraic structure, it is a little bit more tricky because, for instance, finitely generated groups, there are already many of them, yeah, even two generated. So you can go from 1 to 2 and you do not have countably many. The same with finite metric spaces, unfortunately. Yeah? You have a one element space, there's only one. This could be your starting point, your origin. And you have continuum many possibilities to define a distance to a new point. And they are all non-isomorphic because isomorphic means isometric. So in any case, some systems fail this property. Now, the point is, you see this picture disappeared because I moved to the next slide. So in that case, there is a special evolution. Namely, I would say the most complicated one. I call it the absorption property. And it is like this. Actually, I have a picture here. So don't read the part 2 and 3 yet. The picture is at the bottom. You fix any place in the sequence. Like I can maybe mark it in yellow, yeah. You choose your place, you go out, and you are able to come back by the blue. And now the explanation is that the red arrow, which you can see here, is a transition. This is our F actually. And the blue arrow is really a path, so it could really consist of several. This is our G in the definition. So this is the absorption property, which tells you that whenever you go out, so you try to, say, extend your structure in some, let's say, random way, you can always see it somewhere in the sequence. Well, if we talk about, say, metric spaces or Banach spaces, you would have to add some epsilon and really work in a metric enriched category, but I'm not going to talk about it today because the time is really running quickly. Now, the point is that the colimit of the sequence is, let's say, our minimal assumption about the evolution system that the category V, the universe, really has colimits of sequences, which you can always assume, extending it if necessary. So the colimit is unique up to isomorphism. I mean, whenever you have an object which is a colimit of an evolution with the absorption property, it's always the same up to isomorphism, and it is homogeneous with respect to paths between finite objects. And now, okay, so formally, very synthetic thing is that you have a finite object and let's say another one. Here you have our U infinity. Actually, it's enough to say about one, but okay, maybe it's more illustrative if you do it this way. You have a path and you have some infinite path, really. Something like a partial evolution because it doesn't start from the origin. Here you have also some infinite path. Then what happens? You can always get an automorphism extending this diagram. This is what homogeneity means. And if we are in model theoretic structures, yeah, then this U infinity is some set with a structure, and this means that you have one structure, say A, you have another structure, say B, and you have an isomorphism, some embedding actually, not necessarily isomorphism. Then you can always extend it to an automorphism. You know? is what homogeneity says. Now, yeah, as I said, classical Freise limits. This is how Freise in 54 formulated it, that you have a finite language, finite relational structures. We have a class closed under isomorphism, substructures. Then it becomes an evolution system if the origin is the empty structure, transitions are one-point extensions, plus isomorphisms, of course. Then the category could be all homomorphisms, as I said, yeah. And the generic evolution, its co-limit is really, the union is the Freise limit of the class. Okay, I promised in the abstract that I would talk about connections with abstract rewriting systems. Well, at this point, actually, it is not surprising at all, because what is a rewriting system? Some people call it actually a transition system. It depends on the community. So it's just a set with a binary relation, yeah? And this relation means that it is some sort of rewriting, yeah? There is something like term rewriting, graph rewriting, etc. And very in the most abstract setting, it is just this, which from the mathematical point of view is nothing special, yes? When people look at transitive closure of this relation, so now this is actually this partial order. And what is missing here in order to make it an evolution system is you have to choose some element of the set, which could be called a state. And now we have this partial order, so a partially ordered set is definitely a category. Now, the original relation may be called the class of transitions, the set of transitions. So it's a really small category in a way, yes. And we choose our favorite, say, state or object element, yeah. If it is about, say, term rewriting, we choose our complicated expression which we want to rewrite and make it simpler. This will be our origin, yeah. And you have an evolution system by this way, obviously, and it is trivial. Now, this what I don't want to call amalgamation, because it's actually, as it is written here, a system. A rewriting system is locally confluent if for every two, say, rewritings, that the relation here is called a rewriting, yes? So X is related to Y means Y is the result of rewriting X in a single step. Okay, and local confluence means that you start with some place, you use two possibilities, two different rewritings, and you can always come back. And now this is what people call local confluence. And here I say, okay, so this is, again, I want to draw. So we have two possibilities. You see, this is different than amalgamation property, which I defined before. Namely, you have two transitions and you do not require that you close this diagram by transitions, but you are able to have some paths which actually close this, yeah, but they could be pretty long. And it's not hard to see that from this you cannot really prove, you cannot use induction anymore, yes? You cannot use, for instance, if you have two transitions and one transition, yes, to some places, and you want to amalgamate. So for instance, here you get some path of some length, here you have another path of some length, but here, what you do here, you can have a path here, but when you go to infinity, as the induction simply doesn't work. Okay, now confluence means really what we would really call amalgamation property, yeah? That paths can be amalgamated by paths, yeah? So you get from Z by a path, another path, and you can close the diagram maybe by something very long, much longer than the original ones. Never mind, but still a path, which is something finite. And now, yeah, there is a notion of terminating rewriting system, namely the definition is very simple. You try to rewrite and you get stuck always, yeah? So the relation is well-founded or anti-well-founded, if you prefer. Now, for evolution systems, which are really categories, isomorphisms form some sort of obstacles. So we can really have, we always have infinite evolutions because we can use even identities. So a proper definition of being terminating is that you cannot construct an evolution which would consist of infinitely many non-trivial transitions. Okay, so you try to construct an evolution, you are allowed to use arbitrary isomorphisms, but at some point you always get stuck in the sense that you are in some object. Maybe again I draw a picture. So we have, what does it mean terminating? You are going to some object, at some point you get stuck in what sense? The only possible transitions are isomorphisms. So the orange will be isomorphism, maybe more. But moreover, you move by an isomorphism, then also you have the same possibility. Isomorphism, of course, you can always go back, maybe another one, yeah. Actually, this one is also an isomorphism. So no way to move in a non-trivial way. Okay, so this is what is terminating. And yeah, and something classical, kind of celebrated, used to be at least, it says that if you have a terminating rewriting system, which is locally confluent, it's actually confluent. And sort of funny because rewriting systems existed even before theoretical computer science really seriously developed, yes. And it took like almost 40 years until a French mathematician, Gérard Huet, wrote a paper where he gave, let's say, a reasonable, simple proof of this lemma using well-founded induction. The original Newman's lemma is kind of complicated proof, I mean, yeah. And you were used just well-founded induction, yes. So in case of rewriting systems, it is you can. The proof, do I still have time? I don't have really much time. Maybe let me state our version of this, okay? Yeah, maybe the remark a bit later. And what I wanted to say, we have this result also for evolution systems, and it's not just rewriting your proof, okay? We need to deal with isomorphisms. And actually this theorem, as I stated it here, is false. What is really true is this theorem is really true, but it requires one extra assumption on the evolution system, namely, and I'm looking for a good name of this property. So let me draw a diagram illustrating this assumption which is needed. And it is like this. We are in a finite object. We have a finite object and we have a transition. Let's call it T-like transition. And we have an isomorphism, okay? Okay, which is also a transition. So finite amalgamation property would tell us that you can close it by transitions. Local confluence would tell us that we can close it by paths. But what I really need is that we can close it in such a way that this is an ISO and this could be even a path, yeah. So not necessarily a transition. And this property would hold if we have, because what I said, isomorphisms are transitions, and it is very natural to assume that if you have a transition followed by an isomorphism, that it is also a transition, right? But here we would require that the other way around, that we have, let's say, H is an iso, and then F is a transition, which was called tau. Yeah, then from this we would have to conclude that H composition F is a transition. So such a property, if we assume this property, it is quite a natural property, but I don't want to assume it in general because I have some nice examples, or one example I have in mind which fail this property and still makes sense. So I call it isostability or something like that, but maybe you can suggest a better name. So a locally confluent terminating evolution system with this property as some isostable, so I would say isostable, is actually confluent. And in order to prove it, we use indeed a well-founded relation, because since there are no infinite evolutions, then you can define a natural partial order which is well-founded. And we have to play with isomorphisms. So the proof is a little bit longer. Yeah, finally, another variant, which I will not go into the details, is that instead, so let me go back to this. Instead of local confluence, we can assume, for instance, that for every two transitions, we can actually close the diagram by paths, but not necessarily making it commutative. So it would be like being locally directed. And then confluence would be like directedness. Again, a variant of Newman's lemma would hold, but this would be less category theoretic, I would say, that actually we are not interested in commutativity of the diagrams. But we may still look at some quality of the paths. Yeah. By the way, because you may say, what's the difference between terminating evolution systems and terminating rewriting systems? So here, in a rewriting system, people are interested only in the result of rewriting. So for instance, you are from a state Z, you go to the state X, and then you are happy. If we are in the category theory, of course, we can ask how we go. Yes, there are different paths, and not all of them are the same. Yes, there could be many different paths. So how to say, the quality of rewriting plays some role. Okay, so this was it. And yeah, a remark is that actually confluent terminating systems really correspond to phrase classes with finite limits. So you have a finite homogeneous structure when it is a phrase limit of its substructures. And in the end, yes, you see, I had this slide in order to prove and this second variant of Newman's lemma, but I don't have time for that. So let me just mention something which is an application of the ideas, okay, where we could. So I have another paper with a young fellow who just defended PhD, Piotr Nowakowski, where we proved that two quite classical mathematical objects are homogeneous, and instead of proving it directly from the definition, we are simply looking at finite linear structures, points and lines, okay, which are embeddable into these projective planes. And we check the amalgamation property for one-point extensions. Yes, actually the ideology of evolution systems helped to give the proof of these results, yeah, which seem to be new. By the way, these are finite projective planes. So the first one is called the Fano plane, 7 points and 7 lines. And the second one is, I don't remember how many points and lines, but it is modeled by Z3 squared, yeah? And these are the only homogeneous ones. There are no other. Bigger ones cannot be homogeneous, but it's another story. Okay, there are several other topics, possibilities. Let me just mention in the end, because it's now 2:05. So the preprint with several examples is already in the archive. Soon there will be a slightly more extended version with which my co-author is working on some more examples, mainly on graph rewriting and maybe some topological examples as well. And yeah, and about further research on this, since, okay, this new notion can be used simply just playing with it, of course, yeah, but there is something much older, some project which I have with Antonio Aviles from Murcia in Spain, and we also with Ivan Di Liberti, who joined this project like 1 year ago or something. I suppose most of you know Ivan, and we are working on arbitrarily large phrase limits using this language of evolutions, which seems to be the best for the moment, and which generalizes all these cellular categories and things like that. The only thing is that in this particular research, we need, actually I can draw it here, our evolution system now is has to be of the form like we have a category V, we have our class of transitions, we have our origin theta, yes, and we have also some kind of class of commutative squares, which are called tiles, okay? Tiles. So a tile is simply a square, a commutative square composed by transitions. These are all transitions. And we generate bigger squares or rectangles by this way. And absorption property is as before. And why do we need the tiles? Because if we have a really long evolution of some length kappa, and then we go out by a transition, we can come back by a path, yeah? But then we have the composition of two transitions, and you also want to come back. And we have, at some point we reach omega, we reach infinite steps, and we need some properties of those tiles that they behave nicely with respect to colimits, okay? So yeah, typical examples would be push-out squares, yeah, that these commutative squares are push-outs in V. But there are more general examples. So this is some work in progress, which was supposed to be finished a few months ago, but still, we are still working. I'm working on it, yeah, now. Now, something which, again, a few years ago, I talked with some people where abstract stochastic processes is simply that you impose a probability at each finite object, yes? And this makes sense when the system is essentially finite. And there are some preliminary results where with probability 1, we obtain the generic evolution, but not always. We need some, say, normalized some properties which, let's say that the evolution system is, well, not normal, I would say, in some sense stable. Yes, that the number of transitions at some object depends only on its size, not more. Okay, there are several others, other possibilities which I already exceeded 1 hour anyway. And I simply believe that this concept is pretty useful and good. Well, these question marks, it could be, for instance, studying the complexity of generic evolutions, because this is one of my tasks which I have in my current project. Which phrase limits or generic structures are more complicated than the other, how to compare them, yes? And I believe that this framework could help in this case, yeah? Okay, I guess that's all. I had this one last page in case there are any notes to be written or whatever, but thank you for listening, and I guess I apologize for exceeding the time. It's already 10 past 2 and it was supposed to be 1 hour. So thank you.
Okay, thanks to Wieslaw for a very nice talk. And if anyone has any comments or questions, go ahead. No. Go ahead, yeah.
So when you have this category with this classes, with this distinguished class of arrows with transitions, and you have this game building sequences and then data union. So you can look at this as a perfect scheme, right? With this starting object, and then the arrows, and then the arrows out of the arrows. So that's some perfect scheme, and then you have some notion of a basic open set here, which are those infinite sequences that have some fixed starting, and then they continue as they want. So then there's a notion of a Borel set of sequences here, and we know that the Borel game is decided. So the question is that can we put some assumptions on our category as this distinguished class of arrows, so that when you have an object and this fixed isomorphism type, then the set of those sequences which will at the union give that that isomorphism type is a Borel set, so that it would be a decided game.
Okay, so for I don't know if I understand your question correctly, but it is like when you have, so I can draw, yeah, it's we have several transitions here, yeah, and here again, so you really have some sort of a tree, yeah. And of course, amalgamation tells you that it's often goes back. And so, yeah, there is a natural topology on all evolutions, right? Or at least you fix some class so that it becomes a set. Yeah, actually, a neighborhood could be that you have a finite path. Yeah, and then all evolutions that extend. Yeah, so if you have this evolution with absorption property, then you can prove that the isomorphous type of the generic limit or colimit contains a dense G delta in this topology. And this topology is complete. Yeah, it's a complete metrizable space. So yeah, it would make sense to consider more general settings. Yes, for instance, without amalgamation property, right?
So the point here is that what if you don't consider the generic structure, but any object? Then is it still true that the set of those paths that at the union will give that isomorphism type is a Borel set? Because you can also define generic classes of objects, right? That the class of those paths that will give some isomorphism type from that set of isomorph So for example, could we put some assumptions on this category so that every such class of isomorphism types either that or its complement is generic or things like that?
Yeah. Well, this is a good idea to check. Actually, yes. I know that people in Banach space theory are looking at isomorphic type or isometric type of certain spaces. Some of them are not analytic even, and I guess it could be expressed in this setting, except that you need a metric enriched category in that case. This is what I said I will not mention, but finally I mentioned it, that this absorption property could be with epsilons, and you can, for instance, talk about, say, metric spaces or Banach spaces, right? And still ask for generic evolutions. And then this topology would be like, I guess, all evolutions which are epsilon close to something, yeah, at some point, yeah. I'm not exactly sure about details. I think, yeah, it's a good topic for further research, I suppose.
Go ahead. Yeah.
Yeah, a very naive question. So if I think of such an abstract solution system as a non-possible crypto frame of possible worlds, so I use the term frame in a very loose sense, right? So I think of the finite objects as the possible states with respect to my origin and my set of transitions. Is there a rigorous connection to model logic with that interpretation?
Yeah, I don't know. I don't know. It's a good question. Another thing to check, I suppose. I was motivated by the theory of generic structures, yeah, and I found one of my colleagues actually suggested to look at rewriting systems. I would also be interested in connections with automata theory, perhaps. With modal logic, yeah, I don't know enough for the moment, but it's a good idea to check.
Yeah, I can imagine that if you assume enough on your category C, that you can actually define a modality with respect to your evolution system, right? Let's say the first guess would be somehow given an object C in your category C, then you take the modality applied to C would be the finite object with the shortest length, such that every other object with a map into your C factors through that one, something like that. And then maybe you get something like, I mean, I suppose every frame, meaning every process with enough structure, I suppose gives you an evolution system of that form. Then maybe you get a conjunction or something like that. So that you can assign to every model logic, like a initial such evolution system or so.
Okay.
I don't know. Yeah, it's just.
Yes, but thank you very much for your question. I will make a note and see what can be done here. Yeah.
Any other questions here online?
Okay.
Well, if not, then let's thank Wieslaw again.
Thank you. Okay.